Okay, I know this is the moment that you have all been waiting for. We're going to start talking about stoichiometry, and I'm going to try and cover this as fast as I possibly can because there's a lot of material here. So we'll just go over this little bit by bit and try to get through all of it in a reasonable amount of time. There's just a lot here. So we're basically covering all of stoichiometry in this one lesson, all the stuff you learned last year. Okay. So just to remind you, when you have coefficients in a balanced chemical equation, and when I'm talking about coefficients, I'm talking about the numbers obviously in front of the formula in the equation. That's giving us the mole ratio of the reactants and the products, okay? And it's also telling us the molecule ratio, but the most important thing it's giving us is the mole ratio, okay? And so if we know the mass of one substance, we need to convert that into moles. Then we can use the mole ratio in the equation to figure out the number of moles of something else, and then we can go back to the mass of something else, okay? And so your little diagram that you have here, if you've got grams of substance A, then use the molar mass of A, that'll get you to moles of substance A. Then you use the coefficients from the balanced chemical equation, that'll get you to moles of substance B. Then you can use the molar mass of B to get back to grams, okay? So pretty simple to start out with here. Figuring out how many grams of water can be produced from 1.0 grams of C6H12O6 based on the following equation. Okay, this equation is already balanced. We've got our coefficients right here, 6, 6, and 6. And if we have 1.0 grams of C6H12O, then we can calculate the moles of C6H12O, okay? And I know you guys know how to do this. Number of grams in 1 mole, I think it's 180. Let me just double check to make sure on this one. No, that's going to be too high. It's 100, is that right? 12 times 6 plus 12 plus 16. Oh, C6H12O. I'm thinking of C6H12O6. So that's 100. This cancels out. That gives us the number of moles. So 1 divided by 100 is 0.01 moles. And that's the number of moles of C6H12O that we have. Okay. Now, once we have that, we use the coefficients to find the moles of H2O. So 0.01 moles of C6H12O. Oh, it is O6. That's a typo. I apologize. In the equation, it's C6H12O6. Okay. So I think I was right. About 180. Let me just double check here. 12 times 6 plus 12 plus... Yeah, 180. Okay, so that's 180, which is going to make this smaller, 0.00556 moles. Okay. So then 0.00556 moles of C6H12O6, and we want to know the number of moles of H2O. So that goes on the top of our equation. And for every, according to the equation, for every 1 mole of C6H12O6, we have 6 moles of water. Okay? So basically we're just multiplying this number by 6. That's going to give us 0.0333 moles of water. Okay? And then once we know that, we can figure out how many grams of water we have. So 0.0333 moles of H2O. I know this is the long way, but I just wanted to show you the step-by-step process the first time here just to make sure that you remember it. And we're going back to grams of water, and there are 18 grams of water in 1 mole, so we're basically just multiplying this number by 18. And it's going to give us 0.600 grams of H2O. And we need those 2 zeros there because we started with a number that had 3 sig figs, so we need to finish with the number that has 3 sig figs. Alright, so that's that. I think that probably makes sense. Another sample problem here. This time we're not doing it step by step. Solid lithium hydroxide is used in space to remove exhaled carbon dioxide. Alright, so first thing here, and I always said this in class last year, the first thing that you always need with stoichiometry is a balanced chemical equation. Alright, some of you remember that from last year, hopefully. We don't have a balanced chemical equation, so we have to make one, alright? But it's basically telling us what happens here. So it says the lithium hydroxide, which is LiOH, is reacting with gaseous carbon dioxide, CO2, to form solid lithium carbonate, Li2CO3, carbonate's a 2 minus, plus liquid water, H2O. You have to get this right, or you're not going to get the rest of it right, okay? Now let's balance this thing. If we put a 2 here in front of the lithium, how are we doing? 2, 4, 4, 2, 2. I think that takes care of everything, actually. Yeah, looks like it does. So that's all we had to do on that one to balance it. Pretty easy to balance. Now we've got 1.00 grams of lithium hydroxide. And we want to know how many grams of carbon dioxide can be absorbed by 1 gram. Alright, so we've got to go from grams to moles here so that we can compare the two. And in 1 mole of lithium hydroxide, there are 6.941 plus 16 plus 1. About 23.941 grams of lithium hydroxide. And then from there, we're going to go from moles of LiOH to moles of what we're trying to find, which in this case is carbon dioxide, CO2. And the mole ratio here is 1 to 2. For every 1 mole of carbon dioxide, there's 2 moles of lithium hydroxide. And then we want to know grams of carbon dioxide, so we go from moles of CO2 to grams of CO2, and this is about 44 grams in 1 mole. Okay, once we figure all this out, it's going to give us 0.919 grams of CO2. Okay? That's how to work that one out. Again, I think we're probably good on that so far. Now, limiting reactants is the next thing we need to talk about, okay? Because a lot of times they're not just going to give us one of the reactants, they'll give us both, and one of them is going to run out before the other one, okay? So the analogy here, how many cookies can you make? You can make cookies till you run out of one of the ingredients. So if, let's say you're low on sugar, okay? Once you run out of sugar, you can't make any cookies anymore, even if you have extra of the other stuff, okay? The sugar here is the limiting reactant. It's just like that in a chemical equation, a chemical reaction as well. One thing is almost always going to run out before everything else, and then the reaction has to stop because that reactant is no longer present, okay? So the limiting reactant is the reactant present in the smallest amount, but the thing is, you can't compare the masses and figure out which one is present in the smallest amount. You have to change them to moles, and you have to compare the stoichiometry in the equation, okay? So it's whichever reactant you're going to run out of first, okay? And in this example right here, it's the H2, okay? So the O2 would be the excess reagent here. So if you look at this picture that you've got 10 H2 and 7 O2, okay? When they react, we've got 10 H2O and 2 O2s left, okay? And the reason we end up with O2 left over is because there's only 1 oxygen in every water molecule and there's 2 hydrogens, all right? So even though when we start, we actually have more hydrogens than we do oxygen, because when we make water, it's a 2-to-1 ratio, and we're going to run out of hydrogen first, and we have oxygen left over, okay? So here's a sample problem that has to do with that. Alright, so it gives a little explanation here about the Haber process, which they like to talk about on the AP exam. Haber process is basically when you take nitrogen gas and hydrogen gas and you make ammonia. Okay, we're going to see that reaction many times this year. So what they want to know here is how many moles of NH3 can be formed from 3 moles of N2 and 6 moles of H2. Okay, now this is nice because they're already giving us the number of moles. So you might even be able to tell just by looking at this thing which one is the limiting reactant. Okay, and that might be the easiest way to do this one. Now there is another process, and I'll show you that in just a minute when they give us mass. 3 moles of N2, 6 moles of H2, we have twice as much of the H2 as we do of the N2. But if you look up here at the balanced chemical equation, in order for that equation to work, we're supposed to have 3 times as much hydrogen as we have nitrogen, okay, in order for that reaction to go to completion. So, even though we have more H2, H2 is actually our limiting reactant on this one, okay? So H2 is our limiting reactant. It's the one that's going to run out first because there's supposed to be 3 times as much of that based on the chemical equation as there is of the nitrogen, and there's only 2 times as much. So we don't have enough. We're going to run out, okay? So once you know what the limiting reactant is, what it's really asking is how many moles of the product can we make. You always have to use the limiting reactant amount when you're trying to figure out how much of the product you can make, all right? It doesn't matter that we have 3 moles of N2 because not all of the N2 is going to react, okay? But because H2 is the limiting reactant, all 6 moles of the H2 are going to react and be used up. And so we'll use that number, and that's going to give us a clear picture of how much of the product we'll have left, okay? So 6.0 moles of H2. Now again, you could probably do this one in your head, but I'll just write it out, okay? And then moles of H2 on the bottom, we're trying to figure out moles of NH3. There are 2 moles of NH3 for every 3 moles of H2. So when you do that, you should end up with 4.0 moles of NH3. Okay? So hopefully that makes sense. Alright, let's do another limiting reactant problem here. We've got another reaction. Now they're telling us that 3.50 grams of Na3PO4 is mixed with 6.40 grams of BaNO32. Okay, probably the simplest way to do this is to just go ahead and work out both of them and figure out which one makes the greater mass of the Ba3PO42. Okay, not necessarily the quickest way, but probably the simplest way is just to do that. So we know we have 3.50 grams of Na3PO4. Okay. Now, if we assume that all of that gets used up, then we want to see how much of the product we could make. Okay, so we're going to go from grams of Na3PO4 to moles of Na3PO4. And 1 mole, I have to add this up. Let's see, we've got 23 plus phosphorus is 30.974 plus 64 for the 4 oxygen, so about 117.974. Then we're going to go from moles of Na3PO4 to moles of Ba3PO42. And I'm sorry, that's not 1. No, actually it is. I got lucky. Okay, so the coefficient is a 1 right here for the Ba3PO42. The coefficient for the Na3PO4 is a 2, so it's a 1-to-2 ratio. Then we'll go back to the mass of the Ba3PO42. And in 1 mole, we're going to have a lot here. Okay, what I'm calculating for that is 601.938 for the molar mass. Okay, so that's going to give us a mass once we calculate all of this out. Of about 8.92 grams. Oops. Sorry, 8.92 grams. That's sloppy. Ran out of room. So there's that one. Now, I also know that I have 6.40 grams of barium nitrate, BaNO3(2). So I'm going to do the same process again, and I'm going to figure out, okay, how much of the product could I make of the Ba3PO42 if I start with 6.40 grams of the barium nitrate. So with the barium nitrate, whoops, sorry, that's BaNO3(2). And 1 mole of that, we've got taking some shortcuts here on my math, so hopefully you can forgive me for that. Your molar masses might not be exactly the same as what I'm getting. I'm rounding a little bit. Okay, times moles of BaNO3(2). And then again, we're trying to get to moles of Ba3PO42. And again, in 1 mole of Ba3PO42, there are 3 moles of BaNO3(2). And then we already figured out the molar mass for this, so we just got to go from moles back to grams. And that's 601.938. So when you calculate all that, you end up with 4.91 grams of the product. Okay? Now, this amount right here only makes 4.91 grams of the product. This amount right here makes 8.92 grams of the product. So the limiting reactant is the one that makes the least amount of the product. That's the one that's going to run out first. Okay? So your limiting reactant here is the BaNO3(2). Now the nice thing about this is that we already have our answer. Okay? I'm going to run out of room again. This 4.91 grams, that is how many grams of the Ba3PO42 can be formed. Because after that, there's no more BaNO3(2) left. It's all run out. And so the reaction would stop at that point. Okay. Speaking of stopping, I'm going to stop the video there, and we'll do the rest of it, the theoretical yield and the percent yield, on the next video.